Hi friends, see today I am starting a new chapter, that is 10th chapter in your second year physics, that is dual nature of radiation and matter waves. So this is also very important, it comes under modern physics. This chapter comes under modern physics actually. Dual nature, atoms and nuclei, all these comes under modern physics. So in this one, first part, that is dual nature of radiation and matter waves. So actually this complete modern physics, dual nature, atoms and nuclei, all these completely 6 marks are coming in MSET actually. So if you take individually, it may depends upon, sometimes you may give 1 mark or 2 marks from this chapter. But all together from modern physics, from atoms, nuclei and dual nature, total 5 to 6 marks are coming in the MSET. Okay. So first of all, let us see what is the dual nature of radiation matter waves. See, already in light chapter I explained regarding the nature of light given by Newton, Huygens, okay, and other scientists. So whatever Newton told, that is light travels in a particle nature, same thing again will be repeating in this chapter, because from Einstein's, see, according to Einstein, scientist, so he has taken Newton's theory into consideration. Newton's theory, that is particle theory. But it was proved as wave nature, because from Huygens Huygens wave theory or Young's double slit experiment and diffraction, light was proved to be wave nature. Light travels in a wave. But what happened is, again, whatever light was behaved as a wave nature, whatever light has behaved as a wave nature, the interference pattern, diffraction, polarization, again what Einstein has done is taking into consideration Newton's theory, that is particle nature, taking as a particle nature, that is in the form of photons, E is equal to h nu. So considering light as a particle, he has explained the photoelectric effect experiment into the photoelectric effect. So let us see what is this photoelectric effect experiment and what is the main things discussed in this photoelectric effect. Okay, right. So let us start the experiment. Around 1905, I think, around 1905 the experiment was done. Okay, so 1905 photoelectric effect was designed by the scientist Albert Einstein. So let us discuss about this photoelectric effect. Okay, start chedam mari. Right. So before going into this photoelectric effect, first of all we have to know, as I told you just now, light has to be as a particle nature. Light has to be as a particle nature. According to Planck's theory also, energy is equal to h nu or hc by lambda, where h is Planck's constant, c is velocity of light, lambda is wavelength. Okay, so this is the equation. So what is telling is, suppose if you take any metal surface, so we all know inside the metal surface some free electrons are present. We all know inside any metal surface some free electrons are present. Suppose if sufficient energy is given, just now I told you it's a particle nature. According to Einstein, it is not wave nature, particle nature, that is photons, like just like packets, energy packets, okay, photons or quanta packets. So what is saying is, then electron is ejected from the metal surface, and not only that, for different metal there is a work function W is equal to phi. So it varies from metal to metal. This work function varies from metal to metal. For cesium it is one, for another metal it is different. So metal to metal, the way work function value will be different. So what is this work function actually? That means the minimum amount of energy required to remove an electron from the metal surface. అంటే ఎంతైతే మనకి ఎనర్జీ కావాలో E, that minimum energy to remove an electron from the metal surface is called as without any wastage, because as we know inside electrons will be present. So when sufficient energy is given, what happens? They will be colliding. They will be colliding elastically. So inside there will be collisions. So what is saying is, without collision, that means no wastage. No wastage. Wastage should be zero. Electrons should eject from the metal surface. Okay? And those ejected electrons are called as photoelectrons according to Einstein. Those are called as photoelectrons. And the current produced in that is called as photocurrent. And that current produced during the experiment is called as photocurrent. Later on I will explain the experimental setup also. First listen carefully the different types of items here. So first, what is work function? The minimum amount of energy required to remove an electron from the metal surface. For example, I will try to explain for you. For example, this is a small table for you. Energy table. See all the energy, because this energy is the smallest value, it is measured in electron volts, not in joules, please. Okay. Again in next chapter I will be telling this equation. Energy in electron volts. The simplest shortcut formula is 1240 for lambda in nanometers. In the same way, energy in electron volts 12400 when lambda is in angstroms. Because when you substitute H value 6.62, 10 power minus 34, C value 3 into 10 power 10 and lambda value, you will get in joules. But joule is a big unit. Okay, in modern physics we use a very smallest unit. That smallest unit of energy is called as 1 electron volt. And we already, I told in electrostatics, W is equal to VQ. And WV means 1 volt. Q means what? Charge of an electron. So W I can write as simply 1 eV. In the same way, W, what is 1 e charge of electron? That is 1.608 into 10 power minus 19 coulombs into 1 volts. Therefore, this W will become as 1.60 to 10 power minus 19 coulomb volt. So, what is 1 coulomb volt? 1 coulomb volt is again equal to 1 joule. So, therefore, if you equate these two equations, what happens? 1 eV is equal to 1.602 into 10 power minus 19 joules. This is very, very important solving numericals. From electrostatics, we know W is equal to VQ or VE. And same W is equal to again what? VQ and E means charge of electron. So, charge of electron means coulomb volt, again equal to joules. So, W is equal to 1.6 in 10 power minus 19 joules. But this is equal to again what? 1 eV. So, therefore, ఒక electron value ఎంత joules లో అంటే 1.6 into 10 power minus 19 joules. This is how to remember. For example, to explain the photoelectric effect, I will take a small example regarding work function. అదేంటో ఒకసారి చూద్దాం work function. For example, say the emitted energy, what is the energy is coming, E is equal to h mu. Say for example 7 electron volts. So whatever energy felt on the metal surface be 7. Let the work function be phi or W or whatever thing be suppose 2 electron volts. Let the work function be. That means to remove the minimum energy, remove from the electron mean surface is 2 కావాలి, 2 electron volts కావాలి. Now for example wastage అనేది లేదనుకున్నాం. For example here say 0 wastage. So what happens then? What is the value here? 0 wastage అంటే ఇక్కడ kinetic energy ఎంత అవుతుంది? This is called as kinetic energy maximum. Okay, E minus 5, that is 5 electron volts. So here 0 wastage is there. Whenever there is 0 wastage, Ke is maximum. Kinetic energy will be maximum. And the equation is given by E minus 5. This is Einstein's photoelectric effect equation. ఈ ఈక్వేషన్ ఎప్పుడు వాడాలి మీరు? When there is no wastage due to collisions inside the metal. That means the moment the energy felt on the surface, electron is evolving. No collisions and no energy loss. అలాంటప్పుడు మాత్రం ఈ ఫార్ములా వ్యాలిడ్. Ke max is equal to energy felt minus work function. సో ఇక్కడ మీరు చూసినట్టుగా అయితే 0 wastage. So what is kinetic energy? 5. In the same way, let us go to the second example. Serial number ఇది first one. Let us go to for second one. Second one again 7 electron volts felt. Work function 2 eV. Okay. Now let us think here wastage is for example say 2 electron volts wastage. And the moment energy felt on the surface and due to the collisions some heat produced and some energy is wasted. So energy wasted, what is the total value now? 2 plus 2, 4, 7 minus 4, how much? 3 electron volts. So this is the kinetic and second case. Let us go to the third case again. In third case, suppose 7 eV is the this thing and 2 eV is the work function. Suppose in this case, let us take around how much will take? 2 is there. Let us take 4. Let us take 4 eV in the wastage. So what is the total now? 4 plus 2, 6. 7 minus 6, 1 eV. So here the kinetic energy is 1 eV. You cannot take maximum. In this case, you cannot take maximum because wastage is there. Let us go to the next case. 4, 7 eV, 2 eV. Now for example here let us take 5 eV. 5 plus 2, 7. 7 minus 7, 0. Here no kinetic energy. Let us go to the last case. 7 eV, 2 eV, 6 eV. 6 plus 2, 8. So here it is nothing, impossible here. Because here you can see this is 8 electron volts, more than energy. So it is not at all possible in removing the electron here. So strictly speaking, మనం చెప్పాలంటే ఇక్కడ ఏంటి, వర్క్ ఫంక్షన్ అనేది ఒక వాల్యూ, మినిమం వాల్యూ, ఆ వాల్యూని దాటి వెళ్తేనే ఎలక్ట్రాన్స్ విల్ బి కమింగ్ అవుట్. దట్ మీన్స్ it is the minimum amount of energy required to remove an electron from the metal surface. When the moment energy felt, if there is no collisions in the metal surface, it will go with maximum kinetic energy. And that maximum kinetic energy is given by Einstein's equation, that is Ke max is equal to E minus phi. Very, very important equation, please. Okay, written? Very good. Please note down all these things. These are very, very important in solving numericals for MSET. Okay, and NEET examination. And also 1 eV is equal to 1.6 in 10 power minus 19 coulombs. Clear? Right. Now, just now I told you work function, that is minimum amount of energy required to remove an electron. Okay. So here what we are saying, when the Einstein equation is possible, when there is no wastage, then Ke max is written as energy minus phi. According to Einstein's equation, when there is no wastage in the collisions, the moment energy felt on the surface, electrons are evolved. So this equation is valid and this is called as Einstein's photoelectric effect equation, please. Very, very important. This is only possible when no collisions, no wastage, no collisions. If collisions are there, this Ke max will not be possible. Clear? So దీన్ని బట్టి మనకి ఏమర్థమైంది ఈక్వేషన్, if you draw a graph అంటే అర్థం ఏంటంటే here energy, whatever energy felt should be greater than equal to work function. Are you following here? Whatever energy felt on the metal surface, E is equal to in the form of particles, that is photons. Okay, you can see here particles, E is equal to h nu. It should be what here? It should be equal or greater. That then also there is no guarantee that the electrons are coming out, may come or may not come. So E should be greater than equal to phi, work function, then only it may be possible. So therefore what is E here? E is equal to h nu greater than equal to phi, work function. Okay, or here from this you can write in this fashion, nu greater than equal to phi by h. Clear? Nu, that is frequency of the incident light, greater than equal to phi by h. Or this one can become as, you can write down as nu naught. Clear? Nu is greater than equal to phi by h, work function idi. This is work function. H is Planck's constant, 6.62 10 power minus 34 joule seconds. Therefore here phi by h is equal to nu 0 or phi is equal to h nu 0. Okay, now let us draw a graph and try to understand. Very, very important in the examination. Okay, I'll try to draw a small graph now. So many graphs are there in this chapter. Okay, this is x-axis. In x-axis, okay, in x-axis I'll take frequency. I'll take frequency of the incident light on x-axis. Okay, and Ke max, kinetic energy maximum on y-axis. Suppose if you plot a graph for this one, జాగ్రత్త చూడండి ఒకసారి ఈక్వేషన్ Ke max ఒకసారి చూడండి. Ke max is equal to E minus phi. E minus phi. This is Einstein equation. So from this what happens? Ke max is equal to what is E? H nu minus what is phi from the equation? H nu naught. H nu naught. Now if you observe carefully, this nu naught is called as what? Threshold frequency. It is called as threshold frequency. That means below that frequency electrons will not emit from the surface. That frequency is called a threshold or threshold wavelength. Below that wavelength electrons will not remove from the metal surface. Next, in the next thing I will be telling about that also. Threshold wavelength. Threshold frequency and ఏంటి చూడండి ఇక్కడ nu greater than equal to phi by h, which is equal to nu 0. That means the incident light frequency should be equal to that one, should not be less than this one. Then electrons will not come from the surface. Therefore, if you observe this one to a equation y is equal to mx, okay, this is x and this is c. So this is equal to an equation y is equal to mx minus c intercept. So if you draw a graph, you can see. So this is the slope here. This one or this one, anything you can take. Anything can take slope. Okay. So here tan theta, which is equal to m, opposite by adjacent. Opposite by adjacent. So what is slope here? If you observe carefully, this point is called as nu 0 or nu naught, which is called as threshold frequency of the incident light. That means below that what happens? It is going to negative. What is the negative intercept on this one? This one. That is minus h nu 0. Okay? Minus h nu, because y is, you can interrupt, you can see this equation and relate to the y is equal to mx minus c. Y is equal to mx minus c. అర్థమవుతుందా? సో ఇక్కడ ఏమైంది ఇక్కడ? వాట్ ఇస్ దిస్ ఇంటర్సెప్ట్? దిస్ ఇంటర్సెప్ట్ ఈజ్ ఈక్వల్ టు హెచ్ న్యూ 0. H nu 0. This is the intercept. That means below this there is no emission of electrons from the metal surface. This is the intercept made. On y-axis I have taken Ke max, x-axis frequency. So this is what? Threshold frequency. And the slope you can see. What is slope here? Tan theta m. Tan theta is equal to m is equal to h. Planck's constant. The slope here is h, please. Planck's constant. అర్థమవుతుందా మీకు? So tan theta is equal to h here. And mu naught is equal to threshold frequency. And what is the intercept here? Negative intercept. That intercept is nothing but what here? Minus h nu 0. H is Planck's constant. Nu 0 is threshold frequency. Any doubt? Okay? Right. So this is how you will draw the graph for Ke max threshold frequency. Same thing now you can extend for the next one. Adento చూద్దాం. Please copy it. Right. Now same Einstein equation, if you comment on lambda wavelength, we'll see what happens. Same thing if you comment for wavelength, we'll see what happens. ఇదే దాని గ్రాఫ్ ని, if you comment for wavelength, we'll see what happens. Okay, I'm just changing the values here for wavelength. Now let us discuss for wavelength. Let us discuss for wavelength lambda. Now same thing, Einstein equation, Ke max is equal to E minus phi. Phi is work function, E is the energy. Now let us discuss about wavelength. See, as I told just now, whatever energy should be greater than equal to work function. Below that work function value, electrons will not come out. So we know what is E. E is equal to h nu. greater than equal to phi, or nu I can write c by lambda greater than equal to phi, or hc by phi greater than equal to lambda, or lambda is okay, hc is greater కాబట్టి lambda is less than equal to hc by phi. What does it mean? Lambda, see here, hc is greater than equal to hc by phi is greater than equal to lambda, or lambda ain't less than equal to this thing. This one is nothing but equal to lambda 0, which is equal to called as wavelength, threshold wavelength. దీన్ని మనం ఏమన్నా threshold wavelength, please. That means below that wavelength, again electrons cannot remove from the metal surface. This wavelength you can also call as the maximum wavelength. This wavelength you can also call it as maximum wavelength or longest wavelength. Below that value, and hc by phi, which is equal to lambda 0, below that electrons will not come. So once again we'll draw the graph for by using this equation. See here, Ke max is equal to E minus phi. What is E? రాస్తున్నా చూడండి, E minus phi, or Ke max is equal to E h nu or hc by lambda minus phi. But here phi means what? What is phi here? hc by, చూడండి ఒకసారి, what is phi here? Phi is nothing but what? hc by lambda. Check it. hc by lambda కదా phi అంటే. See, hc by lambda is equal to greater than equal to phi, or hc by phi is equal to lambda here. అదొక పాయింట్ ఇక్కడ. E minus phi, energy emitted minus work function here. So finally what we got the value here? Ke max is equal to E minus phi value. Okay. So this one, instead of phi నేను ఏ రాయొచ్చు ఇక్కడ ఒకసారి జాగ్రత్త చూడండి. ఇక్కడ ఈ వాల్యూ ఒకసారి చూడండి. Instead of phi I can write it as hc by lambda 0, please. Check it. Okay na? hc by lambda 0 రాయొచ్చు. ఇక్కడ జాగ్రత్త అబ్జర్వ్ చేయండి. ఈక్వేషన్ y is equal to mx minus c. అర్థమవుతుంది ఇక్కడ ఈక్వేషన్. సి మ్యాథమెటికల్ ఈక్వేషన్, ఇట్ ఈస్ ఇన్ ద ఫార్మ్ ఆఫ్ Ke max ఏదైతే ఉందో అక్కడ, ఇది ఎలా ఉంచండి, Ke max. దిస్ ఈజ్ నథింగ్ బట్ వాట్? y is equal to mx, m ప్లేస్లో hc, x 1 by lambda minus c, entire place c, hc by lambda 0. That means on the x-axis if you take 1 by lambda wavelength on x-axis, and on y-axis if you take Ke max, again you get a graph like this. That means what is this point here? 1 by lambda 0, threshold wavelength, maximum one. Below that what happens, you can see again it becomes negative. And what is the value here? hc by lambda 0. This is the negative intercept you are getting in this case, hc by lambda 0. And this is of course what? hc by lambda 0, phi, work function. Clear? So this is how you can draw the graph. And here what is tan theta? What is slope here? You can see m place లో ఎంత ఉంటుంది? hc, Planck's constant into velocity of light. Okay, here tan theta is equal to hc, please. Clear? So this is how we will be explaining the Einstein's equation. Okay, clear? Right, please copy it. Now I will explain the experiment setup for this one. After these two graphs, let us go to the experiment, please. See, Einstein what he has done is, experimentally it was proved. Let us take an experiment for this one to explain clearly. Okay, and that one is regarding photocurrent. Regarding what is photocurrent, and thereby stopping potential. దీన్నే నెగిటివ్ పొటెన్షియల్ కూడా అనొచ్చు. negative potential. Okay, so for this what we'll do is we'll take a small experiment, that is a vacuum chamber or vacuum tube fully evacuated. So in this what he has taken is two plates, one is cathode, another is anode. Okay, and these are connected to the battery. Okay, with the help of a rheostat, battery with help of a rheostat, and of course an ammeter or a galvanometer, anything you can put it, ammeter or galvanometer or galvanometer or galvanometer to detect the small amount of current, photocurrent. So here a small window is present here, window, quartz window, small window. So from this light is sent, E is equal to h nu. Okay, packets of light felt on this one. So as you know, this is the direction of current actually, positive side. So when the light is incident light for a threshold frequency and threshold wavelength, it is felt on this cathode. This is also called as emitter. This cathode is also called as C, as emitter, and this anode is also called as collector, because those are collecting electrons there. Okay, so here battery with rheostat, galvanometer or ammeter to detect the current. So when the sufficient thing, threshold frequency is there, then you can see electrons are emitting, and then ready to come to the anode, because this is at positive potential. Anode is positive potential, this is negative potential. With respect to this one is 0. So electrons are coming out continuously. But after some time what happens when electrons are coming, here completely they will become so many electrons and space charge is developed. When electrons are completely coming out from the plate, complete electrons to నిండిపోతుంది అక్కడ ఆ ప్లేస్ అంతాని, then it becomes a space charge. So what about the remaining electrons? There is no place to go. See, even though the potential is positive here, because of the jam, just like a traffic jam in the road. So vehicles traffic jam ఎప్పుడు ఏమవుతుంది, ముందు వెహికల్ వెళ్తే కానీ ఈ వెహికల్ వెళ్ళదు. In the same way, if the electrons move, the backside electrons can come. So how these electrons are, jam is cleared now? Yes. So what they'll do is, they'll increase the potential at the anode. When you increase the potential at the anode, what happens? Whatever jam is present, electrons jam is there, space charge, those electrons will be attracted to those plates and electrons will be flowing now. And when the electrons is flowing, the ammeter will be showing current, photocurrent. It will be showing photocurrent, and these are called as photoelectrons. Okay, so thereby continuously whatever electrons are left over here, all will be attracted here to the positive one. Now what we'll do is, after some time, whatever electrons are came here, now no more electrons will be attracted here. See, whatever electrons are present there, only those are attracted by the anode by increasing the positive potential. After some time it reaches to the saturation point. After some time it reaches to saturation point, that current, whatever photocurrent is there, it reaches to saturation point. No more electrons are attracted. That's the point ikkada. Clear? So even if you increase the potential, the electrons cannot come, because already electrons are came here and there is a jam here, traffic jam, like electron jam. So these electrons are attracted by increasing the potential. Okay, now what we'll do is, we'll put this anode, increase the negative potential here, okay, with respect to cathode. Now here what you have done, we'll be increasing the negative potential. When negative potential is kept here with respect to cathode, this negative ఏమవుతుంది, రిపల్ అయిపోతుంది. రిపల్ అయిపోయి పూర్తిగా after some time electrons will stop coming to the anode. When you increase the negative potential here at the anode, after some time no electrons will come, no photons, and there is no photocurrent here. Completely it becomes stopped. That potential for which the electrons are not coming to the anode is called as stopping potential or negative potential. Clear? Okay, so from this experiment what you understood, that means when energy is felt on this cathode emitter, electrons are coming out continuously. After some time it becomes space charge, and there will become a traffic jam here, electron jam here. To clear the jam, we are increasing the potential at the anode, so thereby it is attracting more electrons, and whatever electrons are there here, those are removing from here. And after some time, so what happens? We will increase the potential of A with respect to cathode, negative potential. When negative potential increase, then what happens? No attraction will be there, there will be repulsion. So no more electrons will come here, they will stop coming. And finally, the deflection will not be there. So that potential, whatever potential is there, for which no electrons are coming to the anode, that potential is called as stopping potential or negative potential. So during this process, what is happening? These electrons are having kinetic energy. So this entire energy is converted into work done, that is equal to VQ. This whatever kinetic energy maximum is equal to what? It is equal to the electrostatic potential energy, VQ or VE. Okay, here V I will be using a V0E because this is called as stopping potential, the potential for which no electrons are coming out from the cathode to the anode. So this maximum kinetic energy is equal to the potential energy, electrostatic potential energy, that is V0E, VQ or V0E, where E is the charge of the electron. Clear? So now again we will try to draw a small graph for this one. Clear? So this is a small experiment regarding photocurrent and stopping potential, please. Now we will try to draw a small graph for this one regarding the stopping potential and also the equation also. Okay na? So ఒకసారి graph చూద్దాం మనం. ఈ graph ఏంటంటే ఒకసారి చూడండి. See here on x-axis. On x-axis I'll take potential. On x-axis I'll take potential V. And this is the negative side of the x-axis, x dash. On y-axis, photocurrent I'll take, better, okay, photocurrent. On y-axis I'll take photocurrent I, photocurrent. On y-axis I'll take photocurrent. Now what happens ఇక్కడ మనం ఏం చేసాం in the experiment లో, we are increasing the positive potential at the anode. So what happens? Electrons are attracted. But after one time, certain time, what happened? All the electrons will reach the anode, no more electrons will left over. So it will reach to saturation point. This is called saturation point of current. Saturation point of current. After that, no more electrons will come. Complete electrons will be reaching there. Okay? Clear? So this, if you extend the line here, you are getting this one. This is called as stopping potential or negative potential. And ఏం జరుగుతుంది తర్వాత మనం ఏం చేసాం, at the anode we are increasing the negative potential with respect to cathode. So negative there will be repulsion and electrons will be stop coming to the anode and completely there is stoppage. And for that potential, okay, that potential is called as negative potential or stopping potential. This is the graph for photocurrent versus the potential on x-axis. Okay, even you increase the intensity also, even you increase the intensity also, the potential will be here only, it won't change, please. You can increase the intensity, I1, I2, I3, I4, I5, like that. You may increase the intensity because already it has reached the saturation point, but the negative potential will be here only for different intensities. And ఇక్కడ ఏమవుతుంది, kinetic energy will not change. A number of electrons may come out. If the intensity increasing, number of electrons coming out may increase, but kinetic energy will be same for the electrons. So that is why the potential, whatever stopping potential will be same on the negative x-axis. Clear? Right. Shall I rub it? Okay. Now, after learning about this photocurrent and stopping potential graph, let us learn some more things. That is equation. Okay? Equation. Equation for negative potential or stopping potential. So already just now I told you here Ke max is equal to what I told you? EV0. Very, very important. Whatever kinetic energy of the electrons is converted into electrostatic potential energy. That is nothing but VQ or V0E. But what is Einstein's equation? Einstein's equation is equal to E minus phi. This is what? Einstein's equation for photoelectric. For photoelectric effect. Okay? So from this what happens, you can observe, see, from this equation 1, I can write it as Ke max by E is equal to V0. Ke max by E is equal to V0 kada? Avuna kada? Isn't it? Ke max by E is equal to V0. సో ఇక్కడ ఒకసారి జాగ్రత్త గమనించండి. Ke max అంటే ఏంటి? E minus energy minus phi from Einstein's equation. Okay? సో ఇక్కడ ఇందులోంచి from this equation if write Ke max by E, Ke max by E is equal to V0 kada. So Ke max by E is equal to V0. I can write it as like this. E minus phi by E. Is it okay? Because from here Ke max by E is equal to V0. Just now we obtained an equation. The electron's energy is converted into electrostatics. So Ke max into E minus phi. So E minus phi by E, which is equal to Ke max. This is equal to V0. Ke max by E and V0 kada. So this V0 I can write in this fashion. So V0 is equal to E by E minus phi by E, or V0 E is equal to what? Since E is equal to h nu or hc by lambda, so I can write as hc by lambda minus phi by E. Clear? Now observe carefully this one. Once again we will draw a graph for this one now. Okay? So graph ఎలా ఉంటుందంటే ఇక్కడ Ke stopping potential on y axis, and we will take mx kada 1 by E on y axis, 1 by E or 1 by lambda, hc by lambda kada. Okay, sorry. I can write like this, no? Because E is equal to h nu or hc by lambda into 1 by E. Now what I will do is, okay, hc, I will take lambda on 1 by lambda on x axis, okay, 1 by wavelength on x axis. If I draw a graph for this one, once again, please make a note. Compare this equation again. Y is equal to మళ్ళీ అదే విధంగా రాస్తాను. ఇక్కడ లాంబ్డా రావాలి, ఇక్కడ ఈ రావాలి, ఇక్కడ లాంబ్డా, ఇక్కడ ఈ. Observe carefully. Y is equal to mx minus c. Again you will be getting a y is equal to mx minus c, negative intercept. So the c is what here? Phi by E. And what is slope here? Tan theta. Here slope tan theta is equal to hc by E. Planck's constant, velocity of light by E, charge of electron. Okay? Clear? So this is how you will be getting. And not only that, what is this point? 1 by lambda 0. Threshold wavelength. Below that wavelength again photoelectric effect will not be possible. And stopping potential on the y axis if you take. Okay? So this is how you will be getting the graph. and the intercept on the negative y-axis is getting as phi by E. Phi by E. Clear? So this is how we will be explaining the equation for stopping potential from the experiment. Any doubt? Right. Same thing you can go for, different intensities also. Same graph, you can go for different intensities. Can I rub this one? Right. Clear? See, these equations are very, very, very important while doing numericals in MSET and NEET examinations. Regularly they are asking. Clear? Now, let us go for the last graph, almost last graph you are having. That is graph for photocurrent versus potential. Okay, na? So on y-axis I am taking photocurrent, on y-axis for different intensities, and stopping potential. Stopping potential on x-axis. See, I am varying the intensities here. I1, I2, I3. So different intensity of light. I am changing the intensity of light. Just now I told you, even though you increase the intensity of light, electrons may be increasing, but energy is constant here. For different intensity of light, you can see the photon, that whatever potential, negative potential is same. Even though if you increase the intensity, 1, 2, 3, 4, I1, I2, I3, number of electrons may increase, but I told you energy is constant. Energy of the electrons will not change. So this is the graph in the examination they will be asking. Photocurrent graph on y-axis versus stopping potential on the x-axis, please. Okay, clear? So here whatever potential you are taking is with respect to cathode, please. This potential is with respect to cathode. That means cathode is taken as 0 and this one is increased. Clear? Any doubts? Same equation I told you just now, no? That equation you can apply y is equal to mx minus c. Right? So this is the story about the photoelectric effect equation, other thing. Now last part of the thing left over for you, that is, just now I told you radiation, that is light. Light has particle nature and wave nature. Particle nature, wave nature. Particle nature according to Newton's corpuscular theory, wave nature by Young's double slit, okay, polarization, interference, all those are proved wave nature. But taking particle nature, photoelectric effect is proved. Now same thing, we will go for the last part, matter. Another interesting one, matter waves. Because you know all the sketch pen, body, book, all are matter made up of atoms and molecules. So a scientist named de Broglie, has given a hypothesis. A scientist named de Broglie has given a hypothesis. Just statement, no proof. Hypothesis that matter also behaves as a wave. Because matter already it is particle. But here matter also behaves like a wave. That means, for example, a man is running, a ball is thrown. What is a matter? Ball is a matter made up of atoms and molecules. Even though it is particle, when it is thrown, it behaves as a wave, it seems, according to de Broglie hypothesis. Let us see from one small example whether it is a wave nature or not. That means, when any body is in motion, it will be in a wave nature, he is saying. And not only that, a simple statement he has given that nature has a symmetry. Nature has a symmetry. Nature has a symmetry. Just small statement is given. Okay? And not only that, any particle which is moving, any body which is moving, is in wave nature is saying. Let us try to explain detailedly this one, de Broglie. So according to de Broglie, what he has given is lambda is equal to h by mv or h by p, where h is Planck's constant, 6.62 into 10 power minus 34 joule second. M is mass of the body, v is velocity, and p is momentum, please. P is momentum. Now, because he is saying that particle is also, any body, okay, any body which is moving, and what you are thinking is a particle. Suppose a sketch pen, if I throw it, this is also wave nature. If a person is running, he is also in wave nature. Let us see. For example, take the mass of the person as 70 kgs. Let the velocity be 10 meter per second. He is moving. Now for him, let us calculate the wavelength, wave nature. Lambda is equal to h by mv, or lambda is equal to, what is h value? 6.62 into 10 power minus 34 joule second. Mass you have taken, just small example, 70 kgs, velocity 10. So if you observe carefully, this 6.62 by 7, keep it aside, this is 100. Paiki ఎంత అవుతుంది? 10 power minus 34 and 10 power minus 2. That is how much? 6.62 by 7 into 10 power minus 36 it is. And this is what here? Lambda, meters, MKS units. But meters is a big unit. It cannot be detected. What is 1 angstrom? 1 angstrom is equal to 10 to the power of minus 10 meters. Adotha meeku 1 angstrom, 10 power minus 10 meters is equal to 1 angstrom. Or what is 1 meter? 1 angstrom by 10 power minus 10 meters. So many what happens? Into 1 angstrom by 10 power minus 10 meters. If you take it to the top, what happens? Plus 10. Adi enta avutundi? 10 power minus 36 plus 10, that is 10 power 3 or 2 minus 26. See, whatever may be this value, 10 power minus 26 is not measurable. We can measure only up to 1 angstrom. So that is why a huge person which is having heavy mass, heavy bodies, heavy particles cannot behave as a wave nature. From this it is proved. A heavier body having so much of mass, only elementary particles like proton, alpha particle, electron, all these produce wave nature. Yes, so from his hypothesis. ఎందుకంటే ఈ ఎగ్జాంపుల్తో ప్రూవ్ అయిపోయింది. దిస్ ఇస్ నాట్ డిటెక్టెడ్. 10 power minus 26 angstrom and ఎంత? This is not detected. Only up to this we can detect 10 power minus 10. So that is why, according to de Broglie's hypothesis, heavier body, heavier masses, like like 70 kgs body, 100 kgs body, heavier bodies cannot have wave nature. Only elementary particles like electrons, protons, alpha particles, those will show wave nature, according to this example. Clear? Right. You can try for example for electrons. Okay? You can try for example. Chudandi. For example, what is the mass of electron? 9.1 into 10 power minus 31 kilograms. Let the velocity take 10 power 6 meters per second. What is lambda? H by mv. 6.62 10 power minus 34 joule second. Okay? And mass of ఎంత? 9.10 power minus 31 kgs. Velocity ఎంత? 10 power 6. So if you calculate this, nearly how much you'll get? ఇది పక్కన పెట్టండి. 6.6 to 9.1. What about this one? 10 power minus 34 పైకి తీసుకెళ్తే plus 31 minus 6. So minus 34 minus 6 how much? Minus 40 plus 31. Nearly ఎంత అవుతుంది ఇది? అంతేనా? మైనస్ అంటే నియర్లీ యుల్ బి గెటింగ్ 10 to the power of, చూడండి, నియర్లీ యూర్ గెటింగ్ minus 11 or nearly you are getting 10 to the power of minus 10. Whatever value it may be. So it is what again in angstroms? It will be in angstroms, nearly value. That's చూడండి. ఓకే, అంటే ఇది మీటర్స్లో వస్తుంది మనకి. 10⁻⁻10 మీటర్స్ లేదా 10⁻⁻11 meters you're getting. But 10⁻⁻10 meters is equal to what? 1 angstrom. What is 1 angstrom value? 10⁻⁻10 meters. So this is detected. అందుకే for elementary particles like electron, proton and alpha particle, it behaves as a wave nature. Not like us, heavier bodies cannot behave like a, and it is not measurable. It is not measurable. That is according to de Broglie's concept. Clear? Now last point in de Broglie, okay? Last point according to de Broglie, that is for, I'll give an equation for this one. While doing numericals, it is very, very important. Okay? Right. So according to de Broglie, he is given some equations for smaller particles like electrons. Okay? అదేంటంటే ఒకసారి చూద్దాం. For example, for smaller particles. We all know lambda is equal to h by mv, that is h by p. And we also know the relation between kinetic energy and momentum. Okay, what is that one? P square by 2m is equal to kinetic energy from first year work power energy. Relation between kinetic energy and momentum into ఇది. So from this, what is P? 2mk under root. So put this value here, lambda for smaller particles, h by root over 2mk. See here, k means kinetic energy, please. So this is one equation for smaller particles. Planck's constant by under root 2 into mass of the particle and k kinetic energy. Suppose if same thing if you take for accelerating charge particle. Same thing if you take for accelerating charged particle. Suppose if you same thing if you take for accelerating charged particle. తీసుకుందామా? తీసుకుంటే ఏమవుతుంది? ఫర్ ఎగ్జాంపుల్ చూడండి. See here. For example, here you are applying some potential. For example, this is zero potential. Suppose a charge is there. Let the potential be V. Okay. So here plus charge is going. Potential. You are giving some charge. So charged particle ఏమవుతుంది ఇక్కడ? వర్క్ డన్. So work done is equal to what here? Work done is equal to VQ. Okay. Work done is equal to VQ. That means which is equal to kinetic energy. So ఇక్కడ VQ అంటే ఏంటి? Potential Q అంటే E, charge of electron. So same equation you can apply here for charged particle, h by root over 2 m అంటే ఇక్కడ mass of the electron. ఇక్కడ kinetic energy place లో you can use V, that is V into E, where E is the charge of electron. 1.602 10⁻⁻19 coulombs. Me mass of the electron 9.1 in 10⁻⁻31 kilograms. Okay. If you want it in atomic mass, you can change atomic mass, because 1 am is equal to, again in next chapters I'll tell you in future, that is another at a nuclei. 1 am is equal to 1/12 of a neutral carbonate, that is 1.66 into 10⁻⁻27 kgs or minus 24 kilograms. You can convert that value, and 2 is a constant. So this is for electrons. H by under root 2 me into V. Okay. V is potential. E is also charge of the electron. Okay, well, if you substitute all these values, mass of electron, charge of electron, Planck's constant, there is a shortcut formula for this one. Shortcut formula ఏంటంటే చూడండి. Lambda for electron, please, charged particle, lambda is equal to under root 150 by V. Under root 150 by V. V is potential here, please. Potential. And still you can reduce this equation. 150 nearly చూసుకుంటే 12.27 into root V for smaller particles. Okay. Under root, if you substitute all these values, you will get this one. Again, then if you solve just the 150 square root, nearly 12.26 or 12.27 by root V. Okay. and V is the potential place. Clear? And lastly, we are coming for gas molecules. Last and final, we are coming for gas molecules. For example, gas molecules are there. Already I told you in thermodynamics regarding degree of freedom for kinetic energy of gas molecules and for gas molecules. For gas molecules, how to calculate lambda? So lambda is equal to h by mv అని మనకు తెలుసు. Okay, and we have kinetic energy for as f by 2 kt. I'll put here k as k dash because already kinetic energy is there. Here k dash means Boltzmann's constant. Boltzmann's constant. T absolute temperature. T is Kelvin temperature. And F is degree of freedom. Already I told you regarding this story. Degree of freedom. And generally we take for mono gases. In this case, monoatomic gases will take as 3 value. And diatomic, 5, polyatomic, normal condition 6. If you put it 3 here, value here, kinetic energy is given by 3 by 2 k dash T. And this kinetic energy for what? One molecule. Okay? One gas molecule. One molecule. So put this value here. Okay? ఇందాక మనం రాసుకున్నాం కదా ఏంటది h by what is that one? P square by 2m. P square by 2m is equal to kinetic energy or P is equal to root over 2mk. Okay, ఈ ప్లేస్ లో root over 2mk. In the place of k you can put this one 3 by 2 k dash t. Why I am putting k dash is because this is kinetic energy, this is Boltzmann constant. 2 gets cancelled. So lambda is equal to h by root over m mass 3 Boltzmann constant absolute temperature. Now this also we have a reduction formula for this one. After substituting all those values, Boltzmann constant and mass, okay, mass of the gas molecules. Finally make ఏమొస్తుందంటే formula చూడండి, this formula will reduce to lambda is equal to nearly 25.6 root gram molecular weight into root capital T absolute temperature. Here m is gram molecular weight. Gram molecular weight of the gas, that is mass of the gas by gram molecule. తెలుసు కదా మీకు ఎలా వస్తుందో, గ్రామ్ మాలిక్యులర్ వెయిట్ తెలీదా? ఒకసారి చెప్తాను చూడండి. క్యాపిటల్ M is calculated as, for example, oxygen gas is given, oxygen 816, okay, O2. So 816 కాబట్టి 16 2s are how much? Molecule కదా, oxygen molecule, oxygen atom కాదు. So 816 mass number, 16 2s are 32. So 32 grams you have to put it here. That is how we will calculate the gram molecular weight. And the number of moles ఇచ్చారు అనుకోండి, for example n is equal to mass of the gas by gram molecular weight అనమాట, అది ఫార్ములా. సో ఇక్కడ క్యాపిటల్ M is gram molecular weight, completely multiplying the value and calculating. And T is absolute temperature. 25.6 is the calculated value of the mass, Boltzmann constant, and 3 and Planck's constant by putting all the gas molecules. Okay na? So finally మనకి ఏమొచ్చింది ఇక్కడ 25.6 by under root m into root T, where m is gram molecular weight, T is absolute temperature in kelvins, please. Clear? Right. Now last and final equation to end up this chapter, that is, suppose a charged particle is placed in magnetic field. Suppose a charged particle is placed in a magnetic field. Already I told you in EMI, electromagnetic induction. Suppose this is magnetic field into the board. This is magnetic field into the board. Here a charged particle is there. So immediately what happens? It will make circular motion. It will make circular motion. This will be the velocity. Okay? It will be rotating like this with v velocity. And we know when it is rotating, it is having some radius in magnetic field. The magnetic force is given by what? QVB sin theta. And for maximum value, it is equal to QVB. And what is the centripetal force? mv square by r. This force is balanced by magnetic force. And from this, what is radius? mv perpendicular by qb. So you can utilize this formula also in the place when the charge particle is there. Okay, then what goes mano? So lambda is equal to h by mv. So in that, h by mv. So mv and what is the place of mv? qrb or qbr. So finally you can use the wavelength h by qbr, radius of the rotating charged particle, Planck's constant 6.62, 10 power minus 34 joule second, charge of the electron 1.602 10 power minus 19 coulombs, and B is magnetic field in Weber per meter square or Tesla. So these are the various formulas we'll be using in this chapter. Please make a note, this chapter is a very small chapter. I told you, dual nature of radiation and matter waves. You can take it as a one shot it is. And from this I told you, this complete modern physics, dual nature, atoms and nuclei, ఈ మూడు కలిపి 6 మార్కులు వస్తాయి MCET లో. And from this you can expect 1 mark or 2 marks maybe. Okay? And this is the end of this chapter. Again we will be meeting in the next chapter.